In this lecture, let us talk about FM signal generation by using indirect method. In the last lecture, we discussed the FM signal generation using direct method like voltage controlled oscillator. You have an oscillator, the output frequency is controlled by the input message signal M of t. This is your controlled voltage. Okay, now let us discuss the indirect method in some more detail. So now, what is the basis of an indirect method? It is actually a two-step process. The indirect method is actually a two-step process. In step one, we generate a narrowband FM signal. In step 2, we convert this narrowband FM signal to a wideband FM signal. That's it. Okay. Now, let us first generate narrowband FM signal. Why do we want to do that? Why do we need to generate narrowband FM signal? Because in some sense, narrowband FM signal has a spectrum which is very similar to that of an AM signal, and that fact can be made use of to generate a narrowband FM signal. Okay, so it's easy to generate narrowband FM signal. Its spectrum is more or less similar to your amplitude modulation with carrier. Let us see. Okay, therefore it is very easy to generate. So to be more explicit, let us look at the FM signal or angle modulated signal. X suffix FM of t is equal to A times cosine of omega ct plus phi of t. Okay, and this is the general form of angle modulated signal. Let us choose this function phi of t, okay, as proportional to m of t. So if phi of t is proportional to m of t, then you will get a phase modulation. Recall this, we already discussed this. If phi of t is proportional to m of t, you will get a phase modulated signal. If you choose phi of t proportional to integral of m of tau d tau, then you get a frequency modulation, right? So you have a phase function phi of t, this phi of t, which is controlled by the modulating signal either directly or integral of your modulating signal, right? So now let us expand this relation using cos A plus B formula. So this is going to be A cos of A plus B equal to cos A cos omega t, then cos of phi of t minus A times sin A sin B sin omega t times sin of phi of t. Now for narrowband FM or narrowband angle modulated signal, what you can say about this phi of t, right? Is there any properties that you can ascribe to phi of t when the angle modulation that we are generating or we have is a narrowband in nature? What was the condition for narrowband FM? Beta is small. If that means beta is much smaller than unity. So what does it imply on the nature of phi of t itself? Okay, if beta is much less than 1, then what can you say about phi of t? Phi of t itself will be small. Recall the definition. Okay, so this is also very small. Let's say phase modulated wave. So if beta is very small, the amplitude or the value of phi of t will be very small. Now you recall the definition like sin theta is equal to theta if theta is small, right? Let us use this property. Okay, so in okay, in general for FM signal we said phi of t is equal to beta times omega m times sin omega mt for your phase modulated signal, sorry, frequency modulated signal. And you can substitute here in this expression. See, if m of t is equal to a cos omega mt, then what is phi of t for phase modulation case? It is a times its phase modulation constant kp times cos omega mt. Now if you integrate for frequency modulation, then this is 2 pi kf times a suffix m times omega m times sin omega mt, right? This is your constant which is appearing before the including this before sin omega mt. Therefore phi of t is equal to beta times omega m sin omega mt for fm, and phi of t is equal to beta times cosine omega mt for PM case. Therefore if beta is much less than 1, then phi of t also much less than 1. The amplitude or the value of phi of t will be very small. Okay, so when I say narrowband FM, beta is very small, it implies that phi of t also very small. Therefore from this expression we can write a times cosine omega t times cosine of phi of t minus a times this sin phi t becomes phi of t. You can write phi of t times sin omega t. That's it. Okay. I did a mistake actually here. Why did I do like this? This is divided by omega m, right? So if you integrate, phi of t is equal to 2 pi k suffix f am divided by 2 pi fm. 2 pi will get cancelled. Therefore kf into am divided by fm. So this whole thing we divided as beta times sin omega mt. Recall this definition. Fine. Anyway, that is separate thing that already we discussed. So this is my x of t. Okay. So it implies that if beta is much less than 1, then phi of t also much less than 1 for narrowband angle modulation. If beta is much less than 1, this implies phi of t also much less than 1 for angle modulation. Therefore your x of t is approximately, this is approximate relation, approximately equal to a cos omega t. Then one more assumption we can do. When phi of t is much less than 1, then cos phi of t is equal to 1. Therefore it is 1 minus a times phi of t sin omega ct, using small angle approximation. So this approximation is valid because this is a narrow band signal. Now suppose you want to generate this signal. How do you generate? Can you tell me how to generate this? This is cos omega t, like cos omega ct, carrier signal. Okay, carrier itself, to which you are adding, you are adding to your double sideband. This is your double sideband suppressed carrier, DSBSC. Okay, your phi of t is your message signal, proportional to your message. Okay, So DSBSC signal is added to the carrier. So this is your DSBSC and this one is carrier. So your x of t is approximately a cos omega ct minus, again I am writing the same expression, a of t times sine of omega ct. Instead of using the cosine omega ct, I am using the quadrature carrier. I am using the quadrature carrier. You can think phi of t is your modulating signal. Modulating signal, and in fact phi of t is going to be 2 pi times kf times m of s times ds for FM signal. In fact there is a multiplication factor here, 2 pi kf phi of t, and phi of t is equal to kp times m of t for PM signal. Therefore this phi of t indicates what? Message signal. So recall from your DSBSC, m of t times cosine omega ct. This is what? Here DSBSC signal. Similarly this also indicates DSBSC signal, and this one indicates carrier. That's it. So by using an approximate form of phi of t, you can realize the second term of this equation by a DSBSC modulator. So this can be done with the help of DSBSC modulator. So I don't have to, have any voltage controlled oscillator or any ASW multivibrator. Simply whatever the things I had for AM modulation, the same block I can use it for frequency modulation also. Okay, therefore all I have to do is use the good old DSBSC modulator as a multiplier and generate this signal. And this would be a narrowband FM signal, NB FM signal. The only thing is there is a minus sign, no plus sign here. Okay, so this is a difference. Note down this minus sign. Okay, so that is a difference between your normal AM signal and the narrowband FM signal. In the normal FM signal, AM signal, you will have here also you have plus quantity and here also you have plus quantity. Both are plus, but here this guy is negative. So DSBSC term and the carrier are in the same phase, but here it is out of phase. Maybe let me write down for x AM of t is equal to a cos omega ct plus m of t cos omega ct. So here you have plus sign, and here you have sin omega ct, here you have cos omega ct. That is the difference. These are the two differences. So this is quadrature carrier and this is in phase carrier. Okay, that's it. If two signals have the same spectrum, normally you would like to think that they would be the same signals because the spectra and time domain descriptions are equivalent. One implies the other. So actually they are not identical. In that sense there is a difference. If they were exactly identical, the spectral components are the same in terms of magnitude, but there is a difference in detail. It looks similar, but there is a difference in the detail, and the difference is here use a in phase component in AM and here use quadrature component in narrowband FM. Okay, in narrowband FM, the carrier part, this is my carrier part, and the quadrature carrier part, both are 90 degree apart. Although the basic frequency components remain the same, their relative phase difference are totally different. So that is the that is the phase gets reversed in the case of FM signal. Okay, x narrowband FM of t is equal to a cos omega ct minus, instead of plus I put minus, phi of t times quadrature carrier sin omega ct. This is narrowband FM. Now realization of narrowband FM signal. How do you realize this? How do you realize this narrowband FM signal? Let's say you are generating FM. You start with the m of t. Then the m of t has to be given to an integrator. And this one is given to DSB SC modulator. And this DSB SC modulator is fed by an oscillator. Let's say A times cosine omega ct, A suffix m, and before that you put a 90-degree phase shift in this to modulate the DSB. Therefore here you are giving A times sine omega ct, and this one is A times phi of t times sine omega ct. Because the moment you integrate, then this is equal to phi of t. Now here you are getting A times cosine omega ct. Let me take from here. Okay, and this one both are given to an adder. You put a plus symbol here, and you put a here you put a plus, and here you put minus. This is your narrowband FM signal. So integration is very easy. If you look at here, there is an integration. That integration is very easy to do. Okay, integration and differentiation are things okay, you can easily do using circuits. I am sure you already know that. For example, you can realize approximately an integrator by simple RC elements, right? You take a resistor, simple resistor in series, followed by a capacitor in shunt. So this is my simple integrator, Vi of t, and this one is V0 of t. V0 of t is the integration of your input voltage. Okay, or you could use a op amp to realize the integrator. So integration is something you can do in a very straightforward manner. Okay, and after this integration, followed by a DSB-SC modulator, in which the carrier is 90-degree shifted version of the carrier that you started with. You started with AM times cosine omega ct, and that is shifted by 90-degree. Let's say you have an oscillator which produces A cos omega ct. You phase shift this by 90 degrees. Okay, phase shift by 90 degrees, and give it to DSB-SC modulator. You phase shift this by 90 degrees and give it to the DSB modulator, and these two things, this guy and this guy, produces A times phi of t sin omega ct. And here you directly bring the cosine omega ct and subtract this cosine omega ct, this sideband signal, subtract from the cosine omega ct, and finally you got the narrowband FM signal. It's a very straightforward realization, nothing much in this. Okay, now one important question arises, that what we said, your narrowband FM signal almost similar to AM with carrier. But what did we say? In narrowband FM, no amplitude variation, isn't it? No amplitude variation. But here amplitude is changing. So it is contradicting now. How can I get a constant amplitude from the amplitude changing signal? Originally speaking, in fact there is no amplitude changing. Even narrowband FM also, it is constant amplitude. Okay, because in narrowband FM is an approximation of A times cosine of omega ct plus phi of t. It is an approximation of this guy. Therefore here A is constant. Okay, the amplitude is not changing. Constant in the sense it is independent of the time. Fine. So whereas in AM there is a amplitude variations. Even if we expand this, after that you will get A times cosine of omega ct minus phi of t times sine of omega ct. Okay, it appears that I am generating a signal by amplitude modulation process. So there seems to be a fallacy somewhere. Okay, the fact that you started with constant amplitude, look at their constant amplitude signal, but you are using an amplitude modulation process to generate it. The beauty is you are generating constant amplitude signal. It's a very, very important point to understand. Generating a constant amplitude signal FM signal by using AM modulator. That is a beauty. That is DSB-SC modulator. That means we are not generating an amplitude modulated signal, but indirectly we are generating the frequency modulation using amplitude modulator. So we are not generating wideband FM, but we are generating narrowband FM by using this condition where phi of t is much less than 1. So you may not remember that this is an approximation. Okay, this is not exact equation. So look at this. This is an approximation. So your FM signal is an approximation. But to the extent that this approximation is valid, because we assumed phi of t is much less than 1. So this signal will turn out to be approximate of the constant envelope. Now you can ask me, what is the circumstance under this is valid, equation 1. We said this phi of t must be much less than 1. As long as this condition is satisfied, phi of t is much less than 1, this signal, this equation 1 will tend to have nearly constant amplitude. Okay, so I cannot say it's a constant amplitude. There could be some small amplitude variations of minor margin. That is not an issue. So as long as phi of t is much less than 1, no problem. Okay, because that is the condition under which we have derived this equation. So in narrowband FM there could be some small variations in amplitude. That is a possible problem that you have to keep in mind when you are dealing with the narrowband FM signal. Okay, now let me emphasize again, actually more precisely or more precise way of saying it is phi of t must be much less than 2 pi radians. So that is the more precise way of stating the condition, because that is a condition under which your cos phi of t is 1 and sin phi of t is equal to phi of t itself. Okay, so under this condition you will get a narrowband FM approximation. If this approximation is indeed valid, you will make a duality. That is, if you want to use this method to generate the FM signal. Therefore, what you will get at the output is not a wideband FM signal, but a narrowband FM signal. You have to keep that in mind. So that is why I said it is a two-step process. In the first step, generate narrowband FM. In the second step, you convert this narrowband FM to wideband FM signal. Okay, I convert this narrowband signal into a wideband FM signal. Therefore, step 2 is convert narrowband FM to wideband FM signal. So how do we convert the narrowband FM signal into a wideband FM signal? Any suggestions? What should we do? Let's go back to our definition. What is our definition? X of t is equal to a times cosine of omega ct plus phi of t. The assumption that we made was this phi of t is very small. Okay, if this is very small, then we said narrowband FM. But what we want is, we want a wideband FM. Wideband FM means phi of t must be greater than 1. Therefore, I have to come up with a certain mechanism such that the small value of phi of t to become a large value of phi of t. Okay, so we have to get rid of that assumption that it is very small. Somehow you change that phi of t from small value to a large value. Therefore, I allow phi of t to take large values. So we are stating that phi of t is a small value for narrowband FM. Now we are asking, how can I make it to a large value, right? That is a question which is in front of us. So what I have with me is this signal, okay, that I have generated. Maybe if I approximate this, a cos omega ct minus a times phi of t times sin omega ct. This is what I generated. Okay, now I need to somehow make this phi of t to a large value. Why should I do that? Because I need a wideband FM signal, right? So how do I convert this argument to a bigger value? Look at here, this argument I should make it somehow a large value. How could I do that? Right? So somehow we have to multiply the argument by a cosine function. That is important. Not the cosine function itself. Increase the argument. So you have to multiply the argument of the cosine function. Okay. Of course, in that process, that will also modify your carrier frequency. You cannot simply increase the phi of t alone. If you increase the phi of t, then omega ct also will increases. So this is done through a process called frequency multiplication. Recall this frequency multiplication from your previous lecture when we talked about amplitude modulation. For example, if you have cos square omega ct, what is the frequency in this? 1 plus cos of 2 omega ct by 2. Here the frequency is fc and here the frequency is 2fc. I mean the argument is doubled here, right? Argument is doubled. See, I have a times cos of omega ct plus phi of t. Now if I square this, I will get a squared cos square of omega ct plus phi of t. Let's say phi of t is equal to 0.1. Now after this square, here it is, let's say 0.1. Sorry, 0.1. Now after this, what will happen? This becomes a square times cos square of 2 omega ct plus 2 times phi of t. 1 plus cos of 2 omega ct plus 2 phi t. So initially I had 0.1, now it becomes 2 times 0.1, therefore it becomes 0.2. So if you do the same process one more times, then it becomes 0.4, then it becomes 0.8, then it becomes 1.6. Similarly, this omega ct also increases. 2 omega ct becomes 4 omega ct, then 8 omega ct, then 1.16 omega ct, and so on and so forth. So your frequency multiplier will convert the narrowband FM signal into wideband FM signal, right? Originally, this is my narrowband FM signal. Here my phi of t value is 0.1. If you pass this to a frequency doubler, you pass it through doubler, what will happen? Your phi of t becomes 0.2. Again pass it through doubler, this guy, then it becomes 0.2 becomes 0.4. Then again you pass it to the doubler, it becomes 0.8. Therefore slowly we are moving from a narrowband FM signal into a wideband FM signal through a process what is called the frequency multiplier. So if you have a frequency multiplier, then it's very easy to convert a narrowband FM signal into a wideband FM signal. Therefore the frequency multiplier multiplies the argument of the cosine or sinusoidal function by a certain factor. Again, there are several ways of realizing a frequency multiplier. Okay, I will discuss one of them in a little later, which you have familiar with already. Okay, but something we have already used in some context of generating the AM signal, same kind of things. And this is based on principle of using a non-linear device. Recall that suppose your output V0 is equal to A0 times V of t plus A1 times Vi square of t and plus and so on so forth, or A1 times Vi of t, A2 times Vi square of t plus A3 times Vi cube of t and so on so forth. Using this type of non-linear characteristic of a device, you can generate frequency doubler and tripler, or you can realize frequency doubler and tripler. Therefore nth law device is a physical device. Okay, physical device which produces output which is the nth power of the input. If you have nth law device, then cos omega ct becomes cos to the n of omega ct. So this is in turn cos of n omega ct. Like as I said, cos square omega ct becomes cos 2 omega ct. I am leaving remaining terms 1 divided by 2 and all. Similarly, cos cube of omega ct becomes cos of 3 omega ct plus some terms. I am not writing all those terms, but you can use your trigonometric identity and you can write remaining terms, some other terms. Those terms will not be like a 3 omega ct. Therefore, if power is 3, then 3 times your argument is multiplied. If power is 2, 2 times you are multiplying the argument. If power is n, you are multiplying by n times. Okay, so therefore now you can use the trigonometric identities, and you know that when you make use of those trigonometric identities, among other terms you will get one term corresponding to n times of the argument. So which essentially means you multiply this argument by a factor n that you are looking for. To remove other terms, you simply put a filter. Okay, so to remove other terms, what you have to do is have a band pass filter. So a times cosine of omega ct plus phi of t, give it to nth law device, and the output of the nth law device is given to a band pass filter centered frequency of n times fc, which is passed through the band pass filter. Remaining all are rejected, all other components. This is the only one component that we want at the output of the filter. Therefore E naught of t is equal to, let's say, a dash times cos of n omega ct plus n times phi of t. Let's say if n is equal to 10 or n is equal to 100, then originally my phi of t is, let's say, 0.1. Now if n is equal to 100, then what will happen? Your phi of t becomes 10. That's it. In this case it is narrowband FM, and in this case it is wideband FM. Therefore, through the frequency multiplication process, you are converting the narrowband FM signal into a wideband FM signal. Therefore, the frequency multiplier increases your modulation index by a factor of how much? N. So, originally it was beta, now it becomes N times beta. So, modulation index is increased by a factor of how much? N. So, if you have a square law device, you will get N is equal to 2. If you have a cubic law device, N becomes 3. Usually these frequency multipliers are realized either frequency doublers or frequency triplers. So these two multipliers are very easy to realize using your electronic components. Frequency doublers or frequency triplers. So frequency doubler means N equals 2, frequency tripler means N equals 3. Because typical non-linearity is typically in nth law device have powers associated with the N equals 2 or N equals 3. Non-linearity that you typically get from physical components like your PN junction diode or your PN transistors is of the order of N is equal to 2 or 3. Beyond that, it's difficult to get it. In which case, you can typically build a frequency doublers and a frequency triplers. But it doesn't mean that you can only do multiplication by a factor of 2 or 3. You put them in several such a frequency doublers and triplers in the cascade. Okay, I can put several such a frequency multipliers in cascade. First, I give it to one doubler. Here, let's say phi of t is equal to 0.1. Then it becomes phi of t is equal to 0.2. Put one more doubler. Here, phi of t is 0.4. Put one more tripler. Then it becomes 1.2. That's it. It keep on goes. Okay, I can use any number of them to multiply this argument by an integer n, okay, that I wish to generate. So, of course, in the process, you have modified your carrier frequency also, right? Your carrier frequency originally it was omega ct, now it becomes n times omega ct. Okay, so this also useful. Why is it useful? Because the carrier frequency that I have used in the generation of narrowband FM signal is much smaller. In narrowband FM, the carrier frequency much smaller. I will tell you how much it is smaller. But in wideband FM, your carrier frequency EFC is in the order of 88 megahertz to 108 megahertz. That is a typical standard value for your FM system. Standard value. So initially start with a lower carrier frequency. For narrowband FM, start with a lower carrier frequency because every time you are multiplying, right? Therefore, your carrier frequency becomes larger when you do the frequency multiplication. Okay, because I need higher carrier frequency after the multiplication. Sometimes I may have to do additional multiplication to make sure that I get the carrier frequency that I want and get the modulation index that I want, because they can contradict with each other. Okay. Let us now look at this slightly more detail now. So this is a principle where details can be a little more involved. So this method of realizing a frequency modulator called indirect method was due to a gentleman called Armstrong. Okay, not Neil Armstrong. This is more historical name in the sense older. Okay, this Armstrong was a pioneer in the whole business of making FM popular. In fact, the entire credit for the commercial application of frequency modulation should go to Armstrong. Okay, don't confuse with Neil Armstrong, the person who first entered into the moon. Okay, and this guy is much before this Neil Armstrong, 1940s or 1930s, I guess. He did absolutely pioneering work in this area. So it's another matter. Okay, that he died as a failed man. He struggled a lot to prove the FM is much superior than AM, but at that time, so people invested huge amount of money in amplitude modulation, and nobody is ready to accept his theory and accept his concept. So then finally he committed suicide and he died. And then after his wife went to the court and she filed the case, and finally she won the case. So that's a very tragic story. So he kept on telling people and demonstrating by experimental setup of such stations that FM is far superior than AM in various ways. But people that time, they were not ready to listen. Okay, because people refused to believe him, basically for commercial reasons, nothing else. They invested a huge amount of money on AM. Suddenly, all of a sudden, overnight, if you come and say, okay, those systems are not that much good and FM is very good, means they are not ready to accept now. So they did not want to change the existing AM system because they invested a lot of money on that. So he died as a failed man, but later we picked up his name, of course, and everything worked very well. And anyway, that is just part of sight light when I want to just mention, because some of the things also you should know the history behind how these things were done. People just didn't think about did not think of them overnight and they are start to work. A lot of great effort and huge amount of time they invested on that, and finally they brought out this concept, and that not only on paper and a pencil, but also realizing them as equipment or systems which deployed in practice in this modern era. So a lot of hard work goes into that, which is invisible in the textbook. So I would like you to read more about Armstrong. It's a very interesting story and a slightly tragic one. It's not a very happy ending story. His life, he struggled a lot. Okay, so I think let me stop at this point about the indirect method of generating FM signal. In the next lecture, we will discuss the Armstrong method, that is commercial FM transmission using Armstrong method. Okay, how this narrowband FM signal is generated, and from that how do we do the multiplication, so that finally we'll get the commercial FM transmitter or commercial FM transmission. So let me stop at this point. Thank you very much.